Hello, my student. We'll continue in the same chapter, chapter 8, which is DC motors and generators, part 5. 8.7, the compounded DC motor. This is the last type of DC motor we're going to talk about. Okay, so a compounded DC motor is a motor with both shunt and series field. We have now both fields are connected together. Such a motor is shown in figure 8. This is figure 8. Okay. Dots that appear on the two field coils have the same meaning as the dots on the generator. Current flowing into a dot produces a positive magnetic field. Okay. If current follows into the dots on both fields coil, the resulting magnetic field is the summation of that produces from each coil individually. This situation is known as cumulative compounding. If current follows into the dot on one field coil and out of the dot on the other field coil, the resulting magnetic field is subtracts, okay? Field subtracts. Okay, it is clear, guys, here. If we zoom in here, two figures here, okay? The equivalent circuit of a compound DC motor. We have two types, short shunt connection, and what here, long, okay, short or long shunt connection here for B. This is short and this is what? Long connection. Okay, and this is the dots, guys, here. Okay, this is the dots here. Okay, we are talking about. Also here, this is the dots here. Okay, dots here, you can observe that it will make the summation and subtracts of the resulting magnetic field. Let's move to the next slides. Now we can write the Kirchhoff's voltage law equation for a compounded DC motor. We have VT equal what? EA plus IA multiplied the summation of RA plus RS. RA armature resistance, and RS, this is the series resistance. The currents in the compounded motor are related by, we have also IA equal IL minus IF, and IF will equal what? VT over RF. Also we have the net magnetomotive force and the effective shunt field current in the compounded motor are given by F net equal F, okay, F force plus minus F series minus F armature. F, this is the field. F, the first one will be the for field, and this is for series, and this is for armature reaction. Okay, armature reaction. Okay, so what about here, positive and negative? Okay, we can read here the note where the positive sign is the equation is in the equation is associated with the cumulatively compounded. Okay, for positive we can choose, okay, if we have cumulative compounded we can choose positive sign. Okay, if we have a differentially compounded motor, we can choose the negative sign. Okay, also for I field current, magnetic force effective field equal I field plus minus N series over NF multiply IA minus what? Force armature reaction over NF. Okay. Now let's move to the next slide. Now the torque speed characteristics of a cumulatively compounded DC motor. In the cumulatively compound DC motor, there is a compound compounded of a flux which is constant and another compounded which is proportional to its armature current. Therefore, the cumulative compound motor has a higher starting torque than a shunt motor whose flux is constant, but a lower starting torque than series motor whose entire flux is proportional to the armature current. In a sense, the cumulatively compounded DC motor combines the best features of both the shunt and series motors. Like a series motor, it has extra torque for starting. Like a shunt motor, it does not overspeed at no load. At light loads, the series field has a very small effect. So the motor behaves approximately as a shunt DC motor. As the load gets very large, the series flux becomes quite important and torque speed curve begins to look like a series motor's characteristics. A comparison of a torque speed characteristic of each of these types machine is shown in figure 9a. Now let's talk about the differentially compound DC motor torque speed characteristics. The shunt magnetic field and the series magnetic field subtract from each other. Now, subtract from each other. This means that as the load on the motor increases, okay, IA increases and the flux decreases, okay. The speed of the motor increases. This speed increase causes another increase in the load, which further decreasing the flux and increasing the speed again. Okay, we can see figure 9b. The result is that a differentially compounded motor is unsuitable and tends to run away. This instability is much worse than that of a shunt motor with armature reaction. It is so bad that a differentially compounded motor is unsuitable for any application. Okay, you can see the two figures, guys, here. Okay, the torque speed for the both. A for what, guys, here? For the cumulative compound DC motor, and B for the differentially compound DC motor. As you can see here, this is the cumulative, okay, and this is the shunt, the comparison between the three types. For B differentially, as you can see here, with an increasing of the load, can you see with the speed will go as high, okay. As the torque here increase, the speed will run away. Okay, so it is there is no actually application for this type. Okay. Now let us see how we can control the speed of the cumulatively compound DC motor. The techniques available for the control of speed in a cumulatively compounded DC motor are the same as those available for a shunt motor. Number 1, change the field resistance RF. Number 2, change the armature voltage. Okay. Number 3, change the armature resistance RA. Okay. These are the three methods to control the speed. Now let's solve one example, okay, about this type here. Example 8.8-6. 100 HP 250 volt compounded DC motor with compensating windings has an internal resistance including the series winding, which is 0.04. There are 1,000 turns per pole on the shunt field, 3 turns per pole on the series winding. The machine is shown in figure. Okay, we have the figure here down. And the magnetization curve is shown also here. We have magnetization curve. Okay, this is the curve here. At no load, the field resistance has been adjusted to make the motor run at 1,200 revolutions per minute. The core mechanical and stray losses may be neglected. Now for A, what is the shunt field current in this machine at no load? B, if the motor is cumulatively compounded, find its speed when IA equal to 100 ampere. C, if the motor is differentially compounded, find its speed when IA equal to 100 ampere. Now you have, as you can see guys here, this is the figures of this example here. We have, this is EA, and we have RA with RS, which is 0.04. IL will divide to IA and IF. Okay, we have VT 250, and we have NF, which is 1,000 turn per pole. Okay, we have here the magnetization curve, as you can see. Field current. Okay, this is field current here, and this is what the open circuit internal voltage. This is the voltage. Okay, now let us see the solution of this example. Solution for A, at no load, the armature current is 0. Okay, so the internal generated voltage of the motor must equal to what? VT. Okay, which means that it must be 250 volt. From the magnetization curve, a field current of 5 ampere will produce a voltage of EA 250 volt at 1,200 revolution per minute. Therefore, the shunt field current must be what? 5 ampere. Okay, it is clear guys from where? From the figure here. What is the shunt field current in this machine at no load? Okay, we can check the graph here. At 5 here, 5 ampere. Okay, this is 5. We can go up. Okay, it is what guys here? 250. So at 250, okay, EA equal VT, we get what here guys? We get what? 5 ampere. Okay, so from the graph we can get the result of the current. Okay, now for B, when an armature current of 200 ampere follows, okay, I8 now to 200 ampere, follows in the motor, the machine's internal generated voltage is, we can use the formula here, EA equal VT minus IA multiply RA plus RS. We have VT 250 volt. We have I8 is given from the question 200 ampere. And the summation of RA plus RS, it is given from the question, which is 0.04 ohm. So the result will be what? 242 volt. Now, the effective field current of this cumulatively compounded motor is, now we'll use this formula guys to find the effective what? Field current. As you can see here, IF plus now, because the type is cumulatively plus. I will use what guys here? I will use plus. Okay, N series over NF multiply IA minus, okay, armature reaction over NF. So because guys here, okay, because the question said that the armature here we can neglect here. Can you see here? The core mechanical and stray losses may be what? Neglected. Okay, so here we will cancel this formula here. Okay, we will cancel this one here. We can cancel the armature what reaction, this one. Okay, cancel. So the question, the equation will be now IF, we have IF which is 5 ampere. Okay, IF here 5 ampere plus N series how much? 3 over NF 1000. Okay, from the question. Okay, 3 over 1000 from the question. I8 is given 200, so the answer will be what? 5.6 ampere. Okay guys, this is clear now? Now from the magnetization curve we get what? O, how much? 262 volt at the speed what? 1200. Okay, we will get now, we will check the magnetization curve of the value 5.6. Can we check here the magnetization curve? We get what? 5.6. 5.6 here, 5.6 approximately at this point here. Okay, just will go up. Okay, it will be approximately what here at this point, which is here 262. Okay, now we will come to this equation here. N, okay, N will equal what guys? N equal EA over EAO multiply NO. So 242 volt. Okay, already we calculate this one over 262 from the graph, multiply also from the graph this one from the question 1200 revolution per minute. So the answer will be what? 1108 revolution per minute. Okay, now for the last part in the example here. Okay, if we have, okay, if the machine is now differentially compounded, the effective field current, the same current, now we will use the same current. Now as you can see we will use what? Minus, because we have now differentially IF minus NC over NF. Also we will neglect the here, we will neglect the armature reaction. Okay, so 5 minus 3 over 1000, okay, multiply 200, the answer will be 4.4 ampere. Okay, we will check the magnetization curve. We will get EAO 236 volt at the speed what here? 1200 revolution per minute. Again we'll use the same equation here to find the speed. Okay, 242 over what? 236. So 242 guys, this is we already calculated in part what? B. Now this is from the graph, multiply the 1200 revolution per minute, so the answer will be what? 1230 revolution per minute. Notice that the speed of the cumulatively compounded motor decreases with the load. Okay, while the speed of the differentially compounded motor increases with the load. It is clear now from this example. Okay guys, so this is the end of this lecture of part of explanation of part 5 for the last type of the DC motor, and we will see you inshallah in a new chapter inshallah next week. Thank you for watching this video.